My name is Maximilian Pittner from Robert Bosch and University of Lübeck, and I will present our CVPR paper LaneCPP, Continuous 3D Lane Detection using Physical Priors. Here we show an overview of the method from our last paper 3D SplineNet, which we treat as our baseline. While 3D SplineNet performed state-of-the-art on synthetic data, we observed difficulties when applying it to real data due to several shortcomings. First, the line representation only models the lateral x and height z direction, which limits the representation to lanes progressing in the driving direction. Second, well-known geometric properties about lanes are not considered in the lane representation, although it might help to ensure robust perception behavior. And third, the spatial transformation from front view to 3D space makes a wrong assumption of a flat road plane, while it should actually consider elevations that are typical for road structures. We try to overcome these problems with our new work LaneCPP. Here we show an overview of our architecture. We feed a front view input image into a backbone that extracts multi-scale front view features. These 2D features are lifted to 3D space by our spatial transformation component and are further processed in the 3D branch. From the final 3D feature map, the network head predicts the parameters for our continuous lane representation. Importantly, we utilize prior knowledge about road surface and lane line properties to improve the spatial transformation and regularize the lane representation to gain robust and predictable perception behavior. In the following, we will elaborate on the most important components, starting with the novel lane representation. First, we define a set of straight lines of various orientations and treat these as our initial spline-based line proposals. To determine the geometry of a 3D line, we make the network predict the offsets of the spline control points in the orthogonal direction of the initial proposal, which means one deviation in the xy plane and one in z direction. Consequently, we obtain a flexible real 3D curve function that is capable of modeling almost arbitrary shapes of lines, where we still constrain the geometry to only 2 degrees of freedom to avoid ambiguity, which facilitates the problem of learning lane shapes. We further model the range and visibility of a line as a continuous function using the same spline-based representation. Hence, whenever the visibility is larger than 0.5, the line segment is considered present and visible. This enables us to precisely determine the start and end point of a line in continuous space, and even allows us to learn occlusions. Consequently, the 3 parameters per control point alpha, beta, and gamma k determine the shape and visibility for each line. Next, we'll describe how to incorporate prior knowledge about lane geometry, like line parallelism, surface smoothness, as well as maximum curvature and slope into our lane representation. It turns out that each of these properties can be formulated as loss terms from lane line tangents and surface normals. In particular, minimizing the cosine distance of certain point pairs on neighboring lines enforces parallelism. For certain pairs of surface normals, it enforces smoothness, and for consecutive tangents on a single line, it enforces low curvatures and slopes. Note that these properties can be enforced up to certain thresholds that are carefully chosen. The weighted sum of these terms results in our prior loss term that we use for regularizing the lane line representation. A nice property of our continuous spline-based representation is that the derivatives necessary for the tangents and normals can be computed analytically without losing precision due to discretization. Finally, we'll show a way how to use knowledge about the surface distribution for our spatial transformation. We know approximately how the surface points are distributed with respect to height, so we can sample certain surface hypotheses in this region of interest. To lift features into 3D space, we use these hypotheses to compute intersections with the camera rays and weight these points on the ray according to a learned depth distribution. These weighted points are associated with a top view grid cell, and computing the weighted sum of the points results in the 3D feature vectors that are processed further by the network head. In our experimental section, we proved that each of our contributions leads to a significant gain in performance. Moreover, we show that compared to other methods, LaneCPP achieves the highest F-score and lowest geometric errors in average as well as in each scenario contained in the OpenLane dataset. We also provide a qualitative comparison that further demonstrates the superiority of our LaneCPP visualized in green, in contrast to other methods such as Performer visualized in red. We thank all listeners for their attention.